Hi everyone, I'm Xuezhi Cao from Shanghai Jiaotong University. Today I'm going to introduce our work, joint user modeling across aligned heterogeneous sites. First, let's review the traditional user modeling in existing recommender systems. Viewing from a user side, he or she first takes several actions in the target site. These actions may be microblogging, movie ratings, or online purchases. With these actions, we may employ corresponding user modeling techniques such as collaborative filtering, matrix factorization, and topic models to capture the user's preference within the given scenario, based on which we then take recommendations back to the user. This recommender system has been applied in various scenarios and have brought a great success in improving users' online experience and stimulating user actions. However, despite the success, the limitations still exist. First is the well-known cold start problem, which is this session about. Is when dealing with the newly arrived users, we do not have enough user actions to precisely model the user preferences. Interview processes and cross-domain user modelings are proposed to alleviate the problem. However, the interview process requires additional manual work from the users, and the existing cross-domain researchers mostly work on homogeneous actions. For example, transfer between user ratings towards the books or towards books and movies. Therefore, we do not have a general solution for the heterogeneous actions. Another limitation is the lack of comprehensiveness. Existing user modelings only model part of the user preferences, the most relevant part towards the action in the target site. For example, movie preferences in the movie rating sites. However, we cannot claim that the rest part are totally irrelevant. For example, it might be hard to mine one's political preferences based on only his movie ratings, but it may have some contributions when recommending documentaries or political-related movies. So now let's jump out and have a look at the current situation of how people use the internet. Nowadays, people always participate in multiple sites for different needs. For example, we have Facebook for friendship and Twitter for microblogging and Pinterest for content discovery and etc. Although users have different accounts and in different sites, the underlying preference or the personality should be consistent across these sites. If we can somehow put this information together, we can directly model the underlying general preferences of the user instead of only the preference for the given account. So following this direction, users will only encounter the cold start problem once when he or she first gets in touch with the internet. To make this possible, we first need the sites to be aligned. Fortunately, most sites now allow users to log in or associate with cross-site accounts. In the meanwhile, there are also researches on how to automatically align the sites by mining usernames, social ties, and user profiles. The state-of-the-art approach can achieve accuracy of over 80%, so we don't need to worry too much about getting the sites aligned. So to summarize, our goal in this work is to conduct joint user modeling over multiple aligned sites with heterogeneous actions. The user modeling here is aiming at the underlying general preference of the user instead of only account modeling that capture only the partial preferences for the specific site. The major challenge for this task is the heterogeneousness of the user actions. Fortunately, there are specifically designed algorithms for each of them. For example, topic model for the text and matrix factorization for the rating matrix. But how to integrate these techniques together for joint user modeling is still not a trivial task. Here's a figure explaining what we're trying to do in this work. The blue lines indicates the traditional user modelings forming two isolated recommender circles. And we are trying to add the red lines as well as underlying general preferences shown in the bottom so that we can form an actual user modeling for the user instead of their accounts. So the underlying assumption of our work is that user preferences are to some extent consistent across these sites. Despite its intuitiveness, we also analyze on real data to support the assumption. As preferences are latent instead of explicit, we cannot compare them directly. Therefore, we answer the question that whether users with similar actions in one site are still similar in the other. We model the user actions similarity in two sides by using topic model and GCAS similarity coefficient over the rated movies, and show the result in the figure, which matches with our intuition and supports the assumption. Now we introduce our approach for the joint user modeling problem. We design our model JUMA as a probabilistic graphic model. Here we show the graphic model for its general case. The plate on the right corresponds to each user, and the plate on the left corresponds to each item. The model can be interpreted as each user has a general preference UI. When participating in each site Q, the general preference is transferred by site-specific transferring model TQ into the site-specific preferences PQ of I. Then the actions are generated based on the site-specific item representations and the site-specific action models. To plug a specific site into JUMA framework, we only need to redesign the following three parts: the preferences transferring model, and the item representation, and the user action model. As most online services can be categorized by item-based site and the text-based site, we focus on these two types of actions in this work. For these two types of actions, the most widely used techniques are matrix factorization and topic model, respectively. Therefore, we aim at integrating these techniques into our framework. First, we show the integration for the item-based site. For the preferences transferring, recall that in traditional within-site matrix factorization models, the user's latent factor has a non-informative prior, a Gaussian distribution with zero mean. Now, with the universal general preferences, the site-specific preferences can be transferred from it. We design it to be a linear transformation over the general preferences applied by a Gaussian distribution. And for item modeling, we can just keep the non-informative prior as in the traditional matrix factorization. For user action, we consider each user movie pair as an action, showing that whether the user reads the movie. We then model it by a Bernoulli distribution over the parameter of a sigmoid function applied on the inner product. And for the text-based site, we integrate with topic model, specifically the latent Dirichlet allocation. As the topic model itself is already a graphic model, the integration is very simple. The model structure can be directly plugged into our framework, JUMA. Similar with the matrix factorization we talked about, we can replace the non-informative prior with the prior that transferred from the user's general preferences. So here is an overall look of our framework JUMA integrated with item-based site and text-based site. Here in the middle, we have the general preferences for the users, and on the left, we have the item-based site, and on the right, we have the text-based site. So the following question is how to train the model and learn the parameters. Here we propose a hybrid learning process. We split the graphic model into two weakly connected modules, the user preferences module and the site-specific action module, which are connected only through the site-specific preferences PQ of I. Following Gibbs sampling ideas, we can view the modules as super parameters and iteratively update them one by one until converge. So let's first solve for the site-specific action module. Comparing with the corresponding traditional algorithms, only the parameters are shifted while the structure of the formulas mostly remain the same. Therefore, the inference in traditional modules and in JUMA are mostly the same. Therefore, we can directly borrow the results from the traditional modules and result in the following equations, which I will not go into the details here. If you are interested, please refer to the papers. And for the user preferences module, we need to update the user's general preferences UI, as well as the preference transferring parameters T of Q for each site. Still, we'll follow Gibbs sampling ideas and update them individually according to their posterior distribution condition on the others. Note that the posterior distribution will be depending on the design of the site-specific preferences transferring model. As we do not have the users underlying general preference as ground truth. So for the experiment, we can only evaluate the user modeling through the recommender systems. Specifically, we designed recommender systems using different user modeling techniques as backend to recommend the unseen movies and microblogs in the two sites. We use area under the curve as the key metrics during our experiment. For the item-based side, we compare with inside user modeling techniques, including probabilistic, matrix factorization, and SVD++. We also compare with algorithms that directly borrow the topic model, borrow the topic information from the other side, including the topic-based matrix factorization and the multimodal topic model. And for text-based side, we compare with topic model, which is implemented with latent Dirichlet allocation, and also we compare with collaborative Twitter recommendation, which is operate with the auxiliary information, including Twitter accounts and author profile, and etc. So here is the experimental result for the general cases. First, we show the result for text-based side. From the result, we can show that our approach JUMA achieves relatively improvement of 3.8% and 4.7% comparing to latent Dirichlet allocation when training ratio is 90% and 40% respectively. And the detailed result also indicates that JUMA is more robust to training size. And for advanced and realistic scenario where the site information is available, JUMA Plus also autocompletes the collaborative Twitter recommendation. And for the item-based site, JUMA achieves much better performance comparing to both within-site performance and the joint modeling extended from existing approaches. By this experiment, we show that topic model and matrix factorization can both benefit from integrating with JUMA. For the other untested techniques, we believe that similar improvement can be achieved. Next, we focus on the cold start scenarios. We simulated by limiting the number of actions we use in the training. We show the relative AUC improvement over the users with different number of training actions in the figure. Resulting both sides show that the performance improvement is much better when we are dealing with code users comparing to the non-code users. We achieve a relative improvement of 12.8% for the users with no historic actions in the text-based site and 9.3% in the item-based site. The results indicate that JUMA can successfully leverage cross-site actions to alleviate the cold start problem. Now we focus on the opposite direction of cold start, where the users have more actions than average. Results show that JUMA still outperforms the existing algorithms. For those users, the traditional approaches should be able to precisely model the user's preferences in the target site. The advantage of JUMA here is the comprehensiveness. For example, as we talked about the example between political preferences and the movie ratings, that should be the case here. So that will be all for my talk. Thank you.
So thank you very much for a very nice talk. Have we got any questions? Yes.
Thank you for the talk. I really didn't get where you get data for cross-site users. Yeah.
Yeah, the data we collected data from Douban and Weibo, the largest sites for microblogging and for movie rating in Chinese. And the alignment is gathered from the Douban's user profile link. It directly contains, some users put their Weibo account in their Douban's homepage, so we can get the alignment.
Okay, and do you have many users who don't share cookies?
Yeah, we have the users don't have the alignment.
Yeah. And how do you deal with this?
we don't deal with that.
Okay, thank you.
Can I just follow up on that? Because you said that 80% alignment can be achieved by algorithms.
Yeah.
But 20% wrong sounds like it might be a problem for your algorithm. Did you try to run your algorithm with some errors in alignment in them?
Actually, that 20% might not always be wrong because we don't have all the ground truth for that.
Sure.
So we're not sure what's the gap here.
Right. But do you think your algorithm would be robust to a certain level of alignment noise?
Yeah, the alignment noise would be a problem for this solution, for sure. But I don't think it will jeopardize the performance by too much. Because if we align the two users together, if they are not 100% precise, the users might be similar, so that the algorithm would make that pair of users aligned.
Okay. That actually begs another question that occurred to me while you were showing us the correlation of similarities between sites. Yeah. And you said that that's good evidence that this technique makes sense, but is it possible for them to be too similar as well? Because if preferences are exactly the same between two sites, then you don't get to leverage any extra information.
Actually, the figure I showed is averaged over a group of users. So if we took it, if we split that up, the line wouldn't look that great. So the two sites are not that similar. Okay. It just shows the trend.
Okay. Any other questions? Yes.
I have a question about interpretability. Usually when interpretability, so usually when you have like a topic model, it's hard enough to interpret that, to sort of assign labels, and now you have this joint model.
Yeah.
Have you looked at something like that, of trying to look at the topics that come out, the joint topics?
Okay, let me find it. Yeah, here. The model can be interpreted as each user first have a general preference vector, which is shown on the right, and then when participating in each site, the general preference got transferred by the transferring matrix for the given site into the site-specific preferences, and then based on that site-specific preferences, we generate the actions. So that is the interpretation for the framework.
Okay, thank you.
Time for one more question. Okay. Thank you very much again.
Thank you.